Imagine you're at the controls of a King Air 350, deep into a cross-country flight miles from your destination. Every decision you make, every system you monitor, hinges on a profound understanding of your aircraft.
Absolutely.
And few systems are more fundamental, more absolutely critical than the flow of fuel. It's not just about watching a gauge, it's about knowing how it's stored, where it's going, what kind of fuel it is, and the intricate dance of pumps and valves that keeps those powerful turboprops turning.
That's perfectly put. It's the lifeblood.
Welcome to the Deep Dive, where we cut through the noise and transform complex technical information into clear, truly actionable knowledge.
Glad to be diving in.
Today, we're taking an exhaustive deep dive into the sophisticated fuel system of the King Air 350. We've pulled from the B350 Pilot Training Manual, specifically Section 5F, and other vital documents to give you, our listener, the most comprehensive understanding possible.
Yeah, the PPM is definitely our core source here, along with some related materials. It's all about getting the details right.
Our mission today is straightforward: to equip you with a mastery of this system. By the end of our conversation, you'll have a rock-solid grasp of its architecture, its operational nuances, and how to manage it safely and effectively.
Think of this as your essential shortcut to becoming truly well-informed about this lifeline of the King Air 350.
Exactly. Whether you're studying for that crucial check ride, preparing for a critical operational briefing, or simply fueling your natural curiosity about the incredible engineering behind modern aviation.
Let's get into it.
So let's start at the very beginning. When we talk about the King Air 350's fuel system, my first thought might be a tank in each wing. But I know it's never that simple, is it?
No, it's definitely not that simple. You're right to question that.
Where does all that fuel actually reside in this aircraft?
Okay, so what's truly ingenious about the King Air 350's fuel storage is its distributed architecture. It's not just about cramming fuel in, it's strategic.
Strategic how?
For redundancy. Redundancy, absolutely, but also for structural load management and just efficient fuel delivery. So for each wing, we're actually looking at a main fuel system that's a combination of several distinct parts.
Okay, break that down for us. What parts?
Right. You've got two flexible wing leading-edge bladder tanks. Then there are two rigid box section bladder tanks, plus one integral tank that's actually part of the wing structure itself.
Ah, using the structure itself. Clever.
Very. And perhaps most critically, there's a nacelle tank. Each of these plays a specific role, and they're all interconnected.
So we've got this array of tanks in each wing, all working in concert, but these engines are mounted on the nacelle, which is, a good distance from the wingtip sometimes. How does the fuel from all these different wing tanks actually find its way to the engine?
Especially during high demand phases, right?
Exactly.
Well, that's where a really fundamental principle comes into play. Gravity.
Just good old gravity.
Yep. The primary mechanism for getting fuel from those various wing tanks to the engine is a remarkably simple, yet incredibly reliable gravity feed system.
Huh. So how does that work?
Well, all those wing tanks, the leading edge bladders, the box section ones, the integral tanks, they're all positioned just right and plumbed to gravity feed directly into the nacelle tank.
Okay, so the nacelle tank is the immediate collection point.
Exactly. And as the name suggests, the nacelle tank sits right there, immediately adjacent to the engine itself. And the best part, this gravity flow is entirely automatic.
No pilot action needed.
None whatsoever for this part. The pilot doesn't need to flip a switch or activate a pump for this initial transfer. It's just happening. A continuous passive process ensuring the nacelle tank, the engine's immediate supply, is constantly being topped up as fuel is consumed.
That passive design must eliminate a lot of potential failure points.
It absolutely does. Simplicity where you can have it,
So the nacelle tank really is the immediate reservoir for the engine. What makes this particular tank so central, and what specific design elements ensure it's always ready to feed the engine reliably?
Okay, yeah, the nacelle tank is, without a doubt, the heart of the main fuel system for its respective engine. Its design has a really critical feature, a flapper-type check valve.
A check valve, like a one-way door.
Pretty much. It's a precisely engineered one-way valve. Its job is twofold. It makes sure fuel flows into the nacelle tank from the wing tanks, which is what we want.
Right.
But, and this is crucial, it absolutely prevents fuel from flowing back the other way, out into the wing tanks.
Ah, so no sloshing back during maneuvers or anything.
Exactly. It maintains system integrity, prevents weird fuel redistribution, and just make sure any fuel in that nacelle tank stays put, ready for the engine, without any reverse flow issues. It creates this dedicated, stable pool of fuel right where the engine needs it.
Makes sense. And capacity-wise, how much does this main system hold?
Okay, so each wing in the nacelle main system together holds a usable fuel capacity of 190 U.S. gallons.
190 per side. That's pretty significant.
It is. Forms the backbone of your flight endurance. And when it's time to refill, the filler cap for this main system is pretty convenient. It's on the leading edge of the wing, near the wing tip.
Easy to access.
Yep. And importantly, each filler port also has an anti-siphon valve. It's subtle, but vital.
What does that do?
It just prevents fuel from being siphoned out accidentally, on the ground or even in some weird flight attitudes. Another layer of safety baked in.
Okay, so we've got the main tanks providing that primary fuel supply, automatically feeding the nacelle tank via gravity. But what about those longer missions, where you really need to stretch the legs of the King Air? That's where auxiliary tanks come in, right?
Precisely.
And giving their placement, I'm guessing they can't rely on simple gravity like the main tanks do?
You're absolutely right. This brings up that whole topic of mission versatility, extended range ops. The auxiliary fuel tanks are a distinct, separate system from the mains.
Designed purely for that extra endurance.
Exactly. And they're located differently, strategically placed in a center section tank, kind of tucked into each wing root, closer to the fuselage.
Okay, wing root, so they're lower down.
They are. And you hit the key point. Because they sit lower than the main wing tanks and the nacelle tanks, gravity alone isn't going to cut it. It just won't get that fuel uphill to the nacelle tank.
So that necessitates some kind of active transfer, right? Something has to push it.
Correct. It needs an active transfer mechanism, which means the pilot needs to understand how this fuel gets moved or how the system manages it automatically.
Okay, so if gravity isn't an option for the auxiliary tanks, what's the engineering solution? How does that fuel get from the wing root all the way up and over to the nacelle tank?
This is where they use a pretty clever piece of fluid dynamics, a jet transfer pump.
A jet pump? What's that involve? No moving parts like an impeller.
Right, not like a typical pump you might picture. Instead, each auxiliary tank sump houses one of these jet pumps. It uses a high-velocity stream of what's called motive flow, essentially, pressurized fuel tapped off from the engine-driven primary boost pump.
Ah, so it uses existing fuel pressure.
Exactly. It uses that motive flow to create a low-pressure area, which then kind of sucks or draws the auxiliary fuel up and pushes it over into the nacelle tank.
Ingenious. And is this transfer automatic too?
It is, and the logic is pretty smart. There's a float switch in the sump of the auxiliary tank, constantly checking if there's fuel there.
Okay.
If that float switch says, yep, fuel here, and if there's enough motive flow pressure available to power that jet pump, then the transfer automatically kicks in.
And it consumes the O fuel first?
Generally, yes.
Right.
It's the idea. Use that O fuel early, reducing weight.
Yeah.
Once that float switch drops and indicates the tank is empty, the transfer automatically stops.
So it's designed to minimize pilot workload on those longer flights.
Definitely. Let the system handle it, allowing the pilot to focus on other things.
That automation sounds fantastic for reducing workload. But what happens if, Murphy's Law, despite having fuel in an auxiliary tank, that transfer doesn't happen automatically? What's the pilot's first clue?
That's a critical scenario, and the system's designed for immediate feedback. If there's fuel in an O tank, but for whatever reason it fails to transfer, you'll instantly see an amber annunciator light up on your CAS panel.
CAS being the Caution Advisory Status Panel.
Right. You'll see either L NO fuel XFR or R no fuel XFR. That's your bright amber cue that the automatic transfer has failed.
Okay, so the light comes on. What can the pilot actually do about it? Is there a way to force the transfer?
Absolutely. This is where pilot intervention is key. On the fuel management panel in the cockpit, there's a manual override switch specifically for this situation.
A backup plan.
Exactly. Selecting this switch basically bypasses the normal float switch sensors and directly commands the motive flow valve open, applying power to it. This forces the jet pump to start transferring fuel, regardless of what the automatic sensors are saying.
So it's a direct order. Move the fuel.
Pretty much. But, and this is a crucial operational detail, this manual override is not a set-it-and-forget-it thing.
Ah, okay. What's the procedure?
Once the transfer is complete, or if the automatic system starts working again, the pilot must remember to manually deselect that override switch.
Why is that so important?
Well, if you leave it on, you could have continuous motive flow running unnecessarily, potentially even drawing air into the fuel lines once the tank is empty, or just causing needless wear. You definitely want to switch it off when it's done its job.
Got it. Manual on, manual off. And how much fuel do these O-tanks hold?
Each auxiliary tank adds a usable capacity of 79.5 U.S. gallons. So combined, that's almost 160 gallons extra.
That's a significant range boost.
It really is. Makes a big difference for certain missions. And just like the mains, the filler cap for the auxiliary system is in the wing root, center section of the wing, also equipped with its own anti-siphon valve. Consistent design there.
Right. Okay, so fuel moves from either the main tanks via gravity or the O-tanks via the jet pump into that central nacelle tank, ready for use.
Correct.
But getting it into the engine itself to generate that massive PT6 thrust, that must require more than just sitting there in the nacelle tank. This feels like where the real work of pressure and flow management begins.
You've absolutely hit on the next critical stage. This is where the engine fuel pumps take over. And yeah, understanding their sequence and redundancy is vital for appreciating system reliability.
So what's the first step out of the nacelle tank?
For each engine, there are two main types of pumps working in sequence. First in line is the engine-driven primary boost pump.
Primary boost pump. Is this high pressure?
Actually, no. Don't let the term low pressure fool you into thinking it's unimportant, though. This pump is a real workhorse. It moves a lot of fuel, about 1,250 pounds per hour, maintaining around 30 psi.
So what's its main job if not high pressure?
Its primary role is less about direct delivery to the combustion chamber and more about preparing the fuel for the next pump in line. It operates continuously whenever the gas generator, the N1 section, is turning.
Okay, constantly running when the engine is running.
Right. And it creates this constant head pressure. This pressure is vital because its main function is to prevent cavitation.
Ah, cavitation again, those nasty vapor bubbles in the fuel.
Exactly. Cavitation can disrupt fuel flow, cause erratic engine operation, reduce pump efficiency. Really undesirable stuff, especially at high altitudes where the fuel's boiling point is lower. This primary boost pump is silently, reliably fighting that condition across the entire flight envelope.
It sounds like an incredibly vital, almost silent guardian role for the fuel flow. Now, you mentioned in the outline a specific caution for this pump when using aviation gasoline. Could you elaborate on that? What makes avgas different here?
That's an astute observation. Yes, there's a specific caution tied to avgas. Aviation gasoline has different volatility characteristics compared to standard jet fuel.
Meaning it vaporizes more easily.
Correct. Especially at higher altitudes where the ambient pressure is lower. Because this primary boost pump is essentially sucking fuel from the nacelle tank before pushing it towards the high-pressure pump, it's more susceptible to what's called vapor lock, a severe form of cavitation when operating with avgas at altitude.
So the pump struggles more with the more volatile fuel.
Precisely. It's pulling against less atmospheric pressure, and the avgas itself is just more eager to turn into vapor bubbles. This necessitates stricter procedures when using avgas, which we'll definitely dig into more, particularly regarding the standby pumps.
Okay, so that's the primary low-pressure boost pump. What comes next in line?
Following that primary boost pump is the real powerhouse, the high-pressure, engine-driven fuel pump. This one's mounted on the engine's accessory gearbox, working hand-in-glove with the fuel control unit.
This is the one providing the serious pressure for combustion.
Absolutely. This pump is the final arbiter of fuel delivery to the engine nozzles. And its failure, well, is catastrophic.
How catastrophic.
Immediate and guaranteed engine flameout, no question.
Wow. Okay. That highlights its absolutely critical role. Without it, the engine simply cannot run. Full stop.
Full stop. It's the point of no return for fuel pressure and flow to the engine.
That's a stark reminder of how critical each component is. So that high pressure pump's failure means immediate engine flameout. But what about the primary boost pump, the low pressure one we just discussed? If it fails, is there a backup to prevent that high pressure pump from starving and causing a flameout? Surely the design accounts for that.
You're right to anticipate redundancy. This is exactly where that principle of safety in layers really shines in aircraft design.
So what's the backup?
Each nacelle tank is equipped with a standby electrically powered boost pump.
Ah, an electric backup.
Exactly. This pump is your essential safeguard. Its sole purpose is to jump in and take over, moving fuel directly from the nacelle tank to its respective engine if that primary engine-driven boost pump fails.
So it ensures fuel keeps flowing to the high-pressure pump.
Precisely. It acts as that crucial electrical backup, preventing the kind of fuel starvation that could quickly escalate into an emergency if the primary boost pump quits.
And how does a pilot know when that primary pump has failed and they need to activate the standby pump? What's the indication in the cockpit?
The cockpit gives you an immediate, unambiguous warning. If a primary boost pump fails or just becomes ineffective for some reason, you'll see a distinct red annunciator light.
Red means stop and pay attention.
Definitely. You'll see L fuel press low or R fuel press low light up on the annunciator panel, corresponding to the affected engine.
And what triggers that light?
It's triggered when the fuel pressure downstream of the primary boost pump drops below a critical threshold, specifically 10 psi. It's a clear signal that primary fuel pressure is compromised.
Okay, so the red light comes on, pressure is below 10 psi. What happens next? Does the light stay on?
Well, your immediate action is to turn on the standby boost pump for that side. If the standby pump works correctly, it should restore the pressure. The annunciator light is designed to extinguish when the pressure recovers above 13 psi.
So light off means the standby pump is doing its job.
Correct. But now here's a really critical operational limitation associated with this event. It speaks volumes about the seriousness.
Oh, what's the limitation?
Operating an engine with that red fuel press low, light illuminated, meaning either the standby pump didn't come on or it came on but couldn't restore pressure above 10 psi, is strictly limited.
How limited?
Limited to a cumulative total of 10 hours between overhaul or replacement of the engine-driven high-pressure fuel pump.
Only 10 hours? Wow. Why such a strict limit? Does running without boost pressure damage the high-pressure pump?
It potentially can, yes. The high-pressure pump relies on that positive inlet pressure from boost pump for proper lubrication and to prevent its own internal cavitation. Running it without that positive pressure, or with very low pressure, puts extra strain on it and significantly increases the risk of its failure. That 10-hour limit isn't a suggestion. It's a hard maintenance limit.
It underscores that while the standby pump provides operational continuity if the primary fails, a persistent low-pressure condition is a major issue needing prompt attention.
Absolutely. Backups are for emergencies and getting you safely on the ground, not for indefinitely postponing necessary maintenance.
That 10-hour limit really drives that point home.
Okay, moving beyond individual pump failures, what if there's a larger issue, like a problem with the fuel supply on one entire side of the aircraft, or maybe an unmanageable fueling balance develops? Is there a way to share fuel across the aircraft to keep an engine running?
This brings us to another crucial element of the King Air 350's fuel system design, the cross-feed capability.
Cross-feed? I assume that means feeding fuel across from one side to the other. Essentially, yes. It's a sophisticated design element specifically to address scenarios like single-engine operations, or if you have an issue with, say, a fuel tank or pump on one side.
So how is it physically connected?
Each nacelle tank is connected to the fuel system on the opposite side of the aircraft via a cross-feed line and a cross-feed valve.
Oh, okay.
This means that fuel from either main fuel system left or right can be directed to feed either engine.
That sounds incredibly useful in an emergency.
It's absolutely critical. Imagine you have an engine failure or maybe a tank leak on the right side. You can use the cron feed system to ensure your good left engine can access the fuel remaining in the right wing tanks. It's a literal lifeline for maintaining power to your remaining engine.
So it's designed to route fuel to an engine in need. Now, if you just have a simple fuel imbalance, maybe getting close to that 300-pound limit we'll talk about later. My first thought might be, can I use cross-feed to just level the tanks out? Is that what it's for?
That's a very common question and a really important distinction to make. And the answer is fundamentally no.
No.
Right.
Why not?
While opening the cross-feed valve will obviously move fuel and affect the balance, the system is not designed or intended to be used for transferring fuel from tanks on one side to the tanks on the other solely for balancing purposes.
So its primary job is feeding an engine, not filling tanks.
Precisely. Its fundamental function is strictly to ensure an engine can continue to be fed with fuel, prioritizing propulsion over perfect weight distribution. Trying to use it just for balancing could introduce other complexities, maybe mask a leak, or potentially even exceed system design parameters if not done carefully according to procedure.
Okay, that's a critical point: engine feed, not tank balancing. How does the pilot know when crossfeed is active?
When the crossfeed valve is commanded open, whether to feed the left engine from the right tanks or vice versa, a green fuel crossfeed annunciator illuminates on the panel.
Green for advisory, showing the configuration.
Exactly. It provides instant confirmation of its activation, vital for situational awareness.
And I see the before starting engines checklist actually verifies this system works. Can you walk us through that check?
Sure. It's a neat little sequence. First, you ensure the fuel firewall shutoff valves are open, pushing those handles in. This should extinguish any fuel pressure annunciators that might have been on.
Okay, valves open.
Then, you intentionally turn both standby boost pumps off F. Since the primary pumps aren't running yet, this will cause the red L and R fuel press low annunciators to illuminate.
Which confirms the pressure sensors and lights are working.
Correct. Then you move the crossfeed switch. Let's say you select crossfeed L. This should illuminate the green fuel crossfeed annunciator, and it should extinguish the left fuel press low light because the system is now simulating feeding the left engine from the right side's pressure, which you'd have if the right engine was running.
Ah, proving the crossfeed path is open and providing pressure.
Exactly. Then you switch to crossfeed R, and you should see the green light stay on, the left pressure light come back on, and the right pressure light extinguish. Then you switch it back to OUDO or off-F.
So it confirms the valve operates, the light works, and pressure can indeed cross over.
Precisely. It's a comprehensive check of that critical system before you even start the engines.
And there's also a significant operational limitation tied to crossfeed, isn't there? Something about altitude.
Yes, absolutely. There's a limitation stating that climbing without verified crossfeed capability is restricted to 20,000 feet.
20,000 feet. Why that specific altitude?
It's related to single-engine performance and service ceiling. At higher altitudes, engine performance naturally decreases. If you have an engine failure up high, the ability to access all remaining usable fuel via crossfeed becomes absolutely critical to maintain sufficient altitude and performance for safe flight and diversion. Without guaranteed crossfeed, your effective single-engine service ceiling would be significantly lower. Hence, the 20,000-foot restriction if this system isn't operative. It highlights just how important crossfeed is for high-altitude operations.
That makes perfect sense. Okay, let's shift gears slightly. Beyond just how the fuel moves through this incredibly complex system, what about the fuel itself? Are there specific types approved for the King Air 350? And maybe more importantly, are there critical limitations or, gotchas we need to be acutely aware of when using them? This feels like an area where overlooking a small detail could have monumental consequences.
You've absolutely identified a critical area where knowledge is power. And yeah, overlooking a detail can indeed have significant repercussions. Fuel management goes way beyond just watching the quantity gauges. It really digs into the chemistry and the operational constraints of what you're putting into those tanks.
So let's start with the basics. What are the approved standard fuels?
Okay, the standard commercial grades, the stuff you'll typically find at FBOs worldwide, are Jet A, Jet EA1, and Jet B. These are your robust, reliable, kerosene-based jet fuels designed for optimal performance and engine longevity in turbine engines like the PT6.
Okay, JETA A1B. What about military equivalents?
For military ops, the approved equivalents are JP4, JP5, and JP8. These are military specifications engineered to meet similar performance standards, sometimes with slightly different properties like freezing points or additives depending on the spec. But they're fully approved.
Right. So those are the standard everyday jet fuels. But what if you find yourself in a truly remote location, maybe internationally or facing some unforeseen circumstance, and those specific jet fuels just aren't available? Is there an emergency alternative?
That's exactly the kind of what-if scenario engineers plan for. And yes, in certain emergency situations, aviation gasoline grades avgas can be used.
Avgas in a turboprop. Which grades?
Yep. The approved grades include 80 red, which used to be 88A7, Clip 9196, 100 green, formerly 10013 to well, the very common 100LL blue, and even 15, 145 purple.
Okay, so a range of avgas types are permissible, but sense a big but coming.
Oh, there's a huge but. This is where the critical limitations slam into place. Operation on any grade of aviation gasoline is strictly limited.
How limited?
Limited to a cumulative total of 150 hours between engine overhauls.
150 hours. Cumulative. That's not very much over the life of an engine overhaul.
It really isn't. And it's not a suggestion. It's a hard operational ceiling. The why is multifaceted. Avgas contains tetraethyl lead, which doesn't burn cleanly in a turbine and can cause lead fouling on critical components like turbine blades and fuel nozzles.
Fouling, like deposits building up.
Exactly, which degrades performance and can cause damage over time. Also, avgas has different lubrication properties than jet fuel, which can affect the high-pressure fuel pump and the fuel control unit longevity. Plus, it can impact seals and gaskets over extended periods. That 150-hour limit is there purely to protect the engines from premature wear and significant damage.
Okay, 150-hour cumulative limit. Got it. Any other major restrictions when using avgas?
Yes, there's another vital safety requirement directly linked to avgas use, relating back to our earlier discussion on boost pumps and volatility.
Oh, okay. What is it?
When operating with aviation gasoline, both standby electric fuel boost pumps must be verified as operational before flight for any flights planned up to 35,000 feet.
Both standby pumps must be working.
Must be working. If even one standby fuel pump is inoperative and you're planning to use avgas, flight is strictly prohibited. No go.
Wow, why such a strict requirement? Back to that volatility issue.
Precisely. As we discussed, avgas is more volatile, more prone to vapor lock, especially at altitude. Those electric standby boost pumps provide that essential, continuous positive pressure from the tank to the engine-driven pumps, mitigating the risk of fuel starvation due to vapor formation. With the higher volatility of avgas, having both pumps available and working is considered non-negotiable for safety.
That makes the avgas limitations crystal clear. It's truly an emergency fuel, not something for convenience with serious operational strings attached.
Exactly right. Treat it as such.
So setting aside the type of fuel for a moment, let's talk about managing the fuel we do have on board during flight, particularly regarding balance between the wing systems. I imagine a significant imbalance could really affect the aircraft's handling.
Fuel imbalance is absolutely a critical flight parameter. It's not just about aesthetics on the gauges. It directly impacts aircraft performance, stability, and control.
Is there a specific limit pilots need to stay within?
Yes. The maximum allowable fuel imbalance between the left and right wing fuel systems is 300 pounds. That's about 136 kilograms.
300 pounds maximum difference. What happens if you exceed that?
Several adverse effects can occur. You'll likely experience increased aerodynamic drag as the airplane tries to fly slightly skewed, which burns more fuel and might slow you down. More significantly, it can lead to noticeable control difficulties.
Like needing constant rudder or aileron trim.
Exactly. You might find yourself holding constant control input just to keep the wings level or maintain heading, which really increases pilot workload and fatigue, especially on longer flights. And over the long term, flying with a significant sustained imbalance can actually induce unnecessary structural stress on the airframe, particularly the wing attachments.
So monitoring and managing fuel balance isn't just good practice. It's a continuous, vital task for flight safety and efficiency.
Absolutely. Keep it within that 300-pound limit.
Okay. Now, shifting to the end of the flight refueling. Are there any special considerations or specific procedures we need to follow when putting fuel into the King Air? It sounds like it's not just a matter of sticking the nozzle in and filling her up.
You're absolutely right. Refueling procedures are just as critical as in-flight management, and there are specific sequences designed to protect both the aircraft's structure and the personnel involved.
You mentioned earlier that auxiliary fuel should generally be used first in flight. Does that relate to refueling?
It does in an inverse way.
Mm.
Remember, use O fuel first. When refueling, you should always fill the auxiliary tanks last, assuming you need fuel beyond what the main tanks can hold.
Fill mains first, then top off with O. Why that specific sequence?
You come down to managing the wing bending moment. Think about the weight of all that fuel distributed along the wing.
Right, the wings are supporting that weight.
Exactly. When a wing is heavily loaded with fuel, especially fuel located further out towards the tips or concentrated in one area, it experiences significant bending stress. By filling the main tanks first, which are more distributed across the wingspan and include the nacelle tank, and then adding the auxiliary fuel in the wing root last, you achieve a more balanced and structurally benign load distribution during the refueling process itself. It minimizes undue stress on the wing structure.
That makes perfect structural sense. Load the structure progressively and evenly. Are there other key cautions or checks pilots need to perform during refueling or as part of their daily pre-flight inspection related to fuel?
Absolutely. Several critical points. Firstly, just reinforcing that structural point. Do not fill the auxiliary tanks unless the main tanks are already full. Never O only.
Okay, mains full before O.
Secondly, a seemingly minor detail but important, avoid resting the heavy fuel nozzle directly in the tank filler neck opening for prolonged periods.
Why is that? Risk of damage?
Yeah, it can potentially damage the filler neck itself or the surrounding area over time, which can maybe lead to leaks or sealing issues down the line. Just be mindful.
Good tip. What about personal safety?
Critical. Exercise extreme caution with fuel contact. Jet fuel isn't friendly stuff. If you get any in your eyes, immediately rinse with cool, fresh water for at least 15 minutes and definitely seek prompt medical attention.
And on skin?
If it contacts your skin, wash the area thoroughly with mild soap and water as soon as possible. Prolonged exposure can cause irritation or dermatitis. Safety first.
Always. Now, what about additives, like anti-icing fluid?
Ah, yes. Fuel System Icing Inhibitor, or FSII. Before refueling, you should always confirm with the fuel supplier whether an anti-icing additive has already been blended into the fuel load they're providing.
And if it hasn't, but you need it for your flight condition?
Then it must be properly blended during refueling, and the concentration is critical. The specification calls for a minimum of 0.06% to a maximum of 0.15% by volume.
That sounds like a very precise range. What happens if you get it wrong?
Adding too much can actually be detrimental. It can potentially deteriorate the sealant used in the bladder fuel cells over time, leading to leaks. Adding too little, obviously, won't provide adequate anti-icing protection.
So you need to calculate how much to add carefully.
Correct. And you only add enough additive for the amount of unblended fuel you're taking on to bring the total fuel load within that correct concentration range. You don't just dump some in, check the charts, do the math.
Very important detail. What about pre-flight checks related to fuel already in the tanks?
The most fundamental daily pre-flight task regarding fuel is draining the sumps for contamination.
Checking for water.
Primarily water, yes, but also any sediment or other gunk that might have settled in the tank bottoms. Water is denser than jet fuel, so it collects at the lowest points, the sumps.
And why is getting that water out so critical?
If left undrained, that water can freeze at altitude, forming ice crystals that can block fuel filters, fuel lines, or even interfere with the fuel control unit. Best case, it causes engine issues. Worst case, engine failure. It absolutely has to be drained.
How many drain points are we talking about on a King Air 350?
It's quite comprehensive. For each side of the aircraft, there are 5 tank sump drains, a fuel manifold drain, and a firewall fuel filter drain.
Wow, 7 drains per side. 14 total.
That's right. The firewall fuel filter drain is usually found on the underside of the nacelle itself. The main tank sumps and the pump manifold drains are typically accessible from the underside of each wing. You need to know where they all are and check every single one every day before the first flight.
That's a non-negotiable pre-flight item then?
Absolutely non-negotiable. Diligent sumping is one of the simplest yet most effective ways to prevent major fuel system problems in flight. It's that attention to detail that keeps you safe.
Okay. With all these intricate components, multiple tanks, gravity feed, jet pumps, primary pumps, standby pumps, cross feed, critical limitations, specific refueling needs, how do we as pilots keep a real-time pulse on the health and status of this vital system while we're actually flying? What instrumentation and warnings are there in the cockpit?
That's where the cockpit instrumentation and the annunciator panel become your essential window into the fuel system's operational health. They're designed to give you a clear, concise, and immediate picture of what's happening with your fuel.
So what's the primary display for fuel?
Your primary reference for how much fuel you have on board are, naturally, the fuel quantity indicators, usually gauges showing the pounds or gallons remaining in each wing system.
And these have markings we need to pay attention to.
Absolutely. Critically, there's a distinct no takeoff range, usually indicated by a yellow arc, starting from empty up to 265 pounds per side.
No takeoff range, that sounds pretty definitive.
It is. Taking off with fuel quantity indicating within this yellow arc is strictly prohibited. Full stop. It's a hard limit, ensuring you have adequate fuel for taxi, takeoff, climb, and a minimum reserve for unexpected delays or immediate diversions right after takeoff. Don't even think about going if you're in the yellow.
Okay, clear warning there. What about low fuel warnings in flight?
If the quantity in either main system drops below a certain predetermined threshold during flight, you'll typically see amber, L fuel QDY, or R fuel QDY enunciators illuminate on the CAS panel.
Amber for caution.
Right. It's not an immediate emergency like the red pressure light, but it's a direct alert, prompting your immediate attention to your remaining endurance, your fuel plan, and maybe starting to think about your nearest suitable airport.
So we have the total quantity, the no takeoff range, and a low-level caution. What about monitoring how quickly we're actually using that fuel? That seems crucial for planning.
Absolutely essential. For real-time consumption, you rely on the fuel flow gauges. These are usually part of your primary engine instrument display, providing a dynamic readout, typically in pounds per hour, pph for each engine.
pph per engine.
Correct. This information is indispensable. It allows you to accurately project your endurance, calculate your point of no return if needed, verify your flight plan estimates, and continuously monitor engine efficiency. Any sudden, unexplained spike or drop in fuel flow can be an early warning sign of an engine issue or maybe even a fuel leak, demanding your immediate investigation.
Okay, we've touched on a few warning lights already. The red, fuel press low, the amber, no fuel, XFR. Could you just give us a quick consolidated rundown of the most critical enunciators directly related to the fuel system that a pilot really needs to have burned into their brain?
Certainly. Let's just recap those vital warnings and cautions because they really are the system's way of talking directly to you. First, and arguably most critical for immediate engine health, are those red L fuel press low or R fuel press low Enunciators.
Red. Primary boost pump failure, pressure below 10 psi.
Exactly. Your immediate action is standby pump on for that side. But critically, remember that 10-hour operating limit between high-pressure pump overhauls if the light stays on. It flags a serious maintenance issue.
Got it. What's next?
Next up are the amber LNO fuel XFR or RNO fuel XFR enunciators.
Amber. Auxiliary tank fuel isn't transferring automatically.
Correct. Even if there's fuel present in the O tank, it's not making its way to the nacelle as it should. This light is your cue to investigate check circuit breakers, maybe, and if necessary, use that manual override switch on the fuel panel to force the transfer. It impacts your range, so you need to address it.
Okay. And the last one we discussed.
Finally, the green fuel crossfeed enunciator.
Green. Advisory, crossfeed valve is open.
Right. It just confirms the system is configured for crossfeed, routing fuel from one side to the opposite engine. Not a malfunction warning, but crucial for situational awareness, especially during single-engine ops or if you're deliberately using it per the checklist procedures. These enunciators aren't just lights. They're triggers for specific knowledge and procedures, enabling you to manage any fuel system anomaly effectively and safely.
That's a great summary. It really emphasizes how the enunciator panel translates system status into actionable information. Now, it's becoming increasingly clear that the fuel system doesn't just operate in its own little bubble. It's intricately woven into the broader fabric of the aircraft systems. This is where understanding the system of systems, as you say, truly creates those aha moments for pilots.
That's a fantastic point because an aircraft truly is an integrated machine. No single system operates in total isolation, and the fuel system is a prime example, interacting with several other critical areas.
Like what are some key interdependencies?
Okay, take for instance the oil-to-fuel heater. This is a component within the engine's lubrication system.
Using engine oil heat.
Exactly. It's essentially a heat exchanger that uses the heat naturally generated by the engine oil to warm the fuel before it gets to the fuel control unit.
And why is warming the fuel necessary? Anti-icing.
That's the primary reason. Jet fuel, even though it looks clear, always contains a small amount of dissolved and suspended water. At the cold temperatures found at high altitudes, that water can freeze, forming tiny ice crystals.
Which could block filters or lines, right?
Precisely. A potentially catastrophic blockage. This oil-to-fuel heater helps prevent that by keeping the fuel temperature above freezing. And it's clever, the rate of oil flow through the exchanger actually varies automatically based on the fuel temperature sensed by a thermal element.
So it's self-regulating.
Largely, yes. It constantly works to keep the fuel warm enough to prevent ice formation and also ensures the fuel maintains the proper viscosity for efficient atomization and combustion. It's protecting the engine from ice blockages using the engine's own waste heat.
That's incredibly elegant engineering, using one system's byproduct to enhance another's safety. What about other anti-icing elements directly tied to the fuel tanks themselves?
Good question. There's also the fuel vent heat. This is an often overlooked but crucial part of the overall aircraft anti-icing system.
Heating the vents. Why is that needed?
Well, fuel tanks aren't perfectly sealed. They need to breathe, allow air in as fuel is consumed to prevent a vacuum, and allow air out or in to equalize pressure changes during climbs and descents.
Okay, makes sense.
These vents, which are often just small tubes or openings exposed to the outside air, can be susceptible to icing in the right atmospheric conditions. They're equipped with electrical heating elements to prevent ice from blocking them.
What happens if a vent ices over?
If a fuel vent gets blocked by ice, it can create a vacuum inside the tank as the engines consume fuel. This could potentially lead to fuel starvation even if the gauges show plenty of fuel remaining simply because the pumps can no longer draw the fuel out against the vacuum.
Or worse.
Or worse, a severe pressure differential, either negative pressure from fuel consumption or positive pressure during a rapid descent if the vent is blocked, could actually cause structural damage to the fuel tank itself. So heated fuel vents are a subtle but absolutely key part of safe operation, particularly in icing conditions, activated with the other wing and engine anti-ice systems.
Wow. Another critical but easily overlooked system. Okay, moving closer to the engine itself, the fuel control unit, the FCU. You mentioned it earlier, working with the high-pressure pump. How does it fit into this interconnected web?
The SCU is really the brain of the fuel delivery process, sitting right between the high-pressure pump and the fuel nozzles. It's a highly sophisticated mechanical device, sometimes with hydromechanical and pneumatic inputs as well, directly tied to the fuel system. It receives that high-pressure fuel from the engine-driven pump.
And its job is to meter that fuel precisely.
Exactly. It meters the fuel based on inputs like power lever position, engine speed, N1, compressor discharge pressure, P3 air, and ambient conditions to deliver exactly the right amount of fuel for the desired engine thrust. But it does more than just meter.
Like what?
It contains several key internal components. There's a minimum pressurizing valve, which ensures that sufficient fuel pressure is maintained within the unit itself for correct metering and operation of its internal servos. It also houses the main fuel shutoff valve, providing that positive means of cutting off fuel flow when you command an engine shutdown via the condition lever.
Is that the only shutoff mechanism?
Primarily, yes, for normal operation, and critically, inside the FCU, there's also a minimum flow orifice.
Minimum flow. What's that for?
This tiny but vital orifice ensures a baseline flow of fuel, typically around 90 pounds per hour, pph, in the PT6, is always delivered whenever the engine is operating, even at idle or during rapid deceleration. This is essential for stable engine starting, and crucially, it helps prevent engine flameout during rapid power reductions by ensuring the combustion chamber never gets completely starved of fuel.
A safety net against flameout during transients.
Precisely. It keeps the fire lit, so to speak.
And how do our cockpit controls, specifically the condition levers, interact with this complex FCU to manage the engine start and shutdown?
The FCU state is intrinsically linked to the condition levers in the cockpit. These provide a direct, usually mechanical, command to the FCU. When you move a condition lever to the fuel cutoff position,
Pulling it back into the detent.
right, that action typically depresses a plunger or rotates a cam on the fuel pump or within the FCU itself. This action ports the high-pressure fuel away from the metering section and often back to the inlet of the high-pressure pump, effectively unloading the pump and cutting off the metered fuel supply to the engine nozzles. It's a robust, positive, fail-safe mechanism for engine shutdown. Conversely, moving it to low idle or high idle positions the FCU for normal operation.
Okay, so the FCU meters the fuel. Where does it go from there?
From the FCU, that precisely metered fuel is delivered through fuel manifolds, basically, plumbing to the individual fuel nozzles within the engine's combustion chamber.
How many nozzles are we talking about?
In a typical PT6A-60A, as found on the King Air 350, there are 14 fuel nozzles per engine. These are usually divided into 7 primary nozzles and 7 secondary nozzles.
Primary and secondary. Why the split?
It helps optimize fuel delivery during starting and across different power ranges. The primary nozzles usually handle the initial fuel flow for light-off and low-power settings, providing good atomization at low flow rates. As power increases, the secondary nozzles kick in to provide the additional fuel required for higher thrust levels.
And these aren't just simple sprayers, are they?
Oh, absolutely not. These nozzles are exquisitely designed pieces of engineering. Their job isn't just to spray fuel, but to create a finely atomized, often tangential or swirling spray pattern into the annular combustion chamber.
Why is atomization so critical?
Fine atomization, breaking the fuel into microscopic droplets, vastly increases the fuel's surface area. This allows it to mix rapidly and thoroughly with the compressed air from the engine's compressor section, which is absolutely critical for efficient, rapid, and complete combustion. Good atomization maximizes thrust, minimizes fuel consumption, and reduces harmful emissions.
And I recall the outline mentioning something about cooling.
Yes, that's another clever design feature. Each nozzle typically incorporates a slotted sheath or shroud around its tip. This design serves a dual purpose. It allows some of the cooling compressor discharge air, P3 air, to pass around the nozzle tip itself, preventing it from overheating in the intense environment of the combustion chamber. And this airflow also assists in further atomizing the fuel spray and shaping the flame pattern within the combustor.
Wow. Cooling and atomization combined. It's incredible how much engineering goes into just that final stage of fuel delivery.
It truly is. From the multi-tank storage system designed for capacity and redundancy, to the gravity feeds, the jet pumps, the essential boost pumps fighting cavitation, the critical high-pressure pump, the life-saving cross-feed, all governed by the FCU and delivered through those precision nozzles. It really highlights that system of systems approach. Every single component plays a specific, vital, and interconnected role in safely and efficiently powering the aircraft.
What an incredible journey through the King Air 350's fuel system. We started with that basic question, where does the fuel live? And wow, we've uncovered an entire universe of interconnected systems, critical operational knowledge, and clever engineering solutions.
Indeed. It's been quite the tour. We've navigated from that sophisticated multi-tank storage architecture, understanding how the main wing tanks, those integral tanks, and the nacelle tanks all work together, relying primarily on automatic gravity feed.
Right, and then contrasting that with the distinct role of the auxiliary tanks, needing those active jet transfer pumps because of their lower position, all aimed at extending range.
Exactly. Then we dove into the heart of the delivery system, the crucial sequence of pumps, the engine-driven primary boost pump, tirelessly preventing cavitation.
The absolute necessity of the high-pressure fuel pump for sustained engine operation, where failure means flame out.
And the vital safety net provided by those standby electrically powered boost pumps ready to step in if the primary falters.
And we didn't forget the cross-feed capability, that literal lifeline, allowing either engine to access fuel from either side, understanding its specific purpose for engine feed, not just balancing, and remembering that critical 20,000-foot altitude limitation if it's not operative.
And we really dug into those operational gotchas, didn't we? The specific approved fuels, JTA, JP5, etc., versus the emergency use of avgas.
Highlighting that strict 150-hour cumulative limit for avgas use between engine overhauls, and that non-negotiable requirement for both standby pumps to be operational when flying with it. Huge takeaways there.
Absolutely. Plus, covering those vital in-flight management parameters like staying within the 300-pound maximum allowable fuel imbalance to maintain handling and efficiency, and the meticulous refueling procedures.
Designed to protect structural integrity, like filling the mains first, then the auxiliary tanks last to manage wing bending moment, and getting that anti-icing additive concentration just right.
Can't forget the pre-flight checks either. That rigorous daily draining for water and other contaminants from all 14 of those sump and filter drains. Simple, but so critical.
And in the cockpit, we consolidated our understanding of the key instruments, the fuel quantity indicators with that hard, no takeoff range, the essential fuel flow gauges for monitoring consumption.
And hitting home the meaning behind those critical enunciators. The red fuel press low, the amber no fuel XFR, and the green fuel crossfeed. Each one demanding specific knowledge and action from the pilot.
Finally, we connected all these dots, exploring how the fuel system is deeply intertwined with other aircraft systems, the oil-to-fuel heater using engine heat for anti-icing, the electrically heated fuel vents preventing vacuum or pressure issues, and that incredibly precise fuel control unit translating pilot inputs into exact fuel metering, delivered perfectly atomized through those sophisticated fuel nozzles for efficient combustion.
It really paints a picture of a complex yet elegant and robust system.
For you, our listener, particularly if you're a pilot studying this magnificent aircraft, absorbing these details isn't just about rote memorization for a test. It's truly about grasping the why. Why is that check valve there? Why is that avgas limit so strict? Why fill the O-tanks last?
Understanding the reasoning behind the design and limitations is key.
Because knowing the symptoms of a fuel system anomaly, seeing that red fuel press low light pop up, means you're not just reacting with surprise, you're prepared. You understand the implication, and you can take the correct, timely, and most importantly, safe action based on established procedures.
That knowledge builds confidence and competence.
Exactly. This deep dive, hopefully, has armed you not just with facts, but with the confidence to truly understand and manage the King Air 350's fuel system proficiently, giving you a real, tangible edge in your operational readiness and overall understanding of the aircraft.
Well said. Now, as we conclude this deep dive, maybe a little something to chew on, consider this provocative thought. In an aircraft as versatile and enduring as the King Air 350, where every drop of fuel, every ounce of efficiency, and every layer of redundancy is absolutely paramount, what might be the next generation of innovations in fuel system design?
Where could it go from here?
We've seen the elegance of gravity feed, the cleverness of jet pumps, but could we see entirely new forms of fuel transfer emerge? Maybe solid-state pumping with no moving parts? Or advanced embedded sensor arrays that don't just detect current problems, but actually predict potential fuel system issues like filter clogging or pump degradation before they even become critical.
Predictive maintenance for fuel systems.
Right.
Fascinating.
What kind of truly intelligent fuel management systems might redefine our understanding of aviation fuel logistics in the coming decades? Systems that perhaps automatically optimize fuel burn based on real-time weather and performance, or even reroute fuel internally to counteract damage or leaks autonomously. How could innovations make these already robust systems even smarter, lighter, more fault-tolerant, and more resilient to the unexpected?
That's a truly fascinating question. Looking beyond mechanics to integrated intelligence, definitely something to ponder for the future of aviation design. Thank you for guiding us through this exhaustive, deep dive into the King Air 350 fuel system. It's been incredibly insightful.
My pleasure. It's a fascinating system to explore.
And thank you, our listener, for joining us. Until next time, fly safe, stay curious, and keep that knowledge ignited.